All right, welcome everybody. Please have some food. We have our May Dynamo user group meeting. Welcome everybody. Who's here for the first time? Okay, welcome to the group. If you want to follow our activities and our announcements and see what is coming up, please sign up in our blog. The address is on the screen. My name is Cesar Escalante. I am Design Technology Manager for HOK and coordinator for this group. And we have a couple of great presentations for today. Before we do that, let me run some announcements. Two great speakers today. Masoud Akbarzadeh, he's our remote speaker, connected from New York, I believe. No, from Pennsylvania. And we also have Steve DeWeedy, who's on the house. He's coming from Project Frog, and he's going to show us what is the kind of project that they are doing using computational design methods. Few announcements on activities that are happening around the town. We have a date for the design script workshop. It's going to be on June 24th. That's a Saturday, and it's from 9 to 3. So if you're interested to learn about design script, that is the written line coding that Dynamo uses, feel free to sign up. The announcement is going to come next week. Three teachers, Armand Halidou, who's not here today, myself, and Enrico Shiona. And it's going to be limited to 20 people, so when you see the announcement, sign up early. There's going to be a nominal cost, $20 or $25, so stay tuned for that. Other announcements, our colleague Marcelo Gambelluri, he has a running podcast related to computational design called Simply Podcast. The address to see his announcements and his activities are on the screen. He always has really nice speakers, so follow him if you want to. There is a new Dynamo Fundamentals class coming up in June, presented at the Boston Facade Conferences, led by Colin McCrone. He used to be one of our founder members here at SFDUG. And Kyle Martin, who is the coordinator of the Boston Dynamo user group. To register, it's on the screen, facadeplus.com agenda. There is a local event coming up as well. This is the first edition of the Advanced Computational Building Design 2017. I don't know if you've heard about this before. I think there was a version of this in the East Coast and in Europe, but this is the first time they are presenting it on the West Coast. It's going to be August 28th and August 30th, and the price ranges from $500 to $3,000. It's not a cheap one, but it has a couple of work sessions and hands-on training, and several of our members and former members are going to be our speakers. So Young Lee is going to be presenting, and so does Jeremy, if you remember, those were part of our committee. It's going to be at the Sheraton Fisherman World Hotel. If you want to register and you're interested about it, the screen is on the screen. It's not so much about picks and clicks and the workflows, but it's more about how to implement design technology, computational methods within organizations of different sizes. So the topics are pretty nice. Thank you for our sponsors, Gensler for the go-to webinar and IDA for the food. If you're interested to speak here, feel free to send us an email, but send us a note, show what you're doing. Next month in June, we're going to feature the work by Woods Bagot. We have two speakers. Pardis Mirmalek She's the BIM manager at Spraga. And Brian Rinkley, who's the digital practice leader in New York, presenting remotely as well. The topic is, what is Dynamo about? For somebody who's never used Dynamo and somebody who wants to understand what the possibilities are. This is not going to be here in HOK. It's going to be at the AIA San Francisco. So register when you see the announcement. Okay, so it's a pleasure for me to introduce Dr. Masoud Akbarzadeh. I'm just going to quickly read some of his bio. He's assistant professor of architecture and structures and advanced technology, and he's the director of polyhedral structural laboratory in the University of Pennsylvania. He holds a PhD of Institute of Technology and Architecture of ETH Zurich, and 2 degrees from MIT, Master in Science in Architectural Studies and Computation, and a Master of Architecture as well. He has a degree in Earthquake Engineer and Dynamics of Structure from Iran University Science of Technology, and a Bachelor of Science in Civil Engineering. And Steve DeWitt, who's going to follow his presentation, he has he's been manager with 20 years of experience in Autodesk products and AEC terms. He's a certified professional, and he's been in Project Frog for about 3 years, developing their main platform, and that's what he's going to be talking about after Dr. Masoud's presentation. So with that said, let me make Masoud the presenter.
Okay. All right. Do you have my voice?
We do. We have a little bit of feedback.
Okay. Is my voice clear?
Now it is.
Okay, great. Hello, everyone. Shall I start?
Yes.
Okay, great. Thank you so much for the introduction. It seems like a really nice event's coming up. I hope I would be able to join the lectures as well. Well, thank you so much for the invite. It's a pleasure to present for you guys. I wish I had this chance to be in person there and present for you. Unfortunately, it didn't happen. Hopefully, next time. My name is Masoud Akbarzadeh. I'm not going to introduce myself more. The topic that I'm going to talk about is going to be a slightly different, let's say, approach to design. So far, as an architect or engineer, if you hear about design, you imagine forming and pulling and pushing and descriptive geometry and so on and so forth. But I'm going to talk about design in another environment, which I call it design the force. So keep calm and use the force. To just give you a brief introduction about the topics that I'm going to talk about, I'm going to introduce the topic and talk a little bit about different methods of structural form finding. I'll talk about principle of equilibrium of polyhedral frames, which is the basis and the foundation of my current research. I'll show you some spatial funicular form findings based on that, give you some examples and applications, and introduce a computational implementation that I did for this. And I'll finish everything by showing some examples of the recent material investigation that we have been doing. Okay, so let's start. Well, there are a lot of great examples of structures in the history of building construction that they achieve, first of all, really expressive forms from architectural point of view, but at the same time they achieve really high structural performance, and they could minimize the use of materials. What all these great examples have in common is basically the form. So in fact, if you have the right form, you can achieve a lot and maximize the structural performance while minimizing the use of material. For instance, in this case, Guastavino was using a specific form for his shells that are built only using 2 layers of brick with really, really high structural capacity. So finding form is an interesting topic in the field of structural design and well, the current research in the field of architecture. Generally speaking, there are 3 main categories of form finding in structural design. So the first category is physical form finding methods, another category is numerical methods, and the third category is graphical methods. I'm going to briefly talk about each category and then build up the case and explain why I'm actually shifting towards graphical methods rather than numerical and physical. So let's just start with physical form finding. Probably this is the most overused example of physical form finding in any lecture around the world. If there is a structural engineer who's talking about the efficiency, they start with this idea of a hanging chain. That first time was proposed by Robert Hooke in 1676. Basically, he mentioned that if you hang a chain based on its own weight, it's going to have the most efficient form based on the given boundary condition. It means that the only force, the internal force in your system would be tensile, and the amount of moment basically in your system would be minimized. If you reverse that form, you get the best form in compression. And this is a very important let's say, premise that they started with, an idea that became the most important part of designing many important buildings. So, for instance, so this, in 1748, once they built the St. Peter's Dome in Rome, they realized that there's some cracks at the bottom of the dome. But because they didn't use any type of specific form finding method to come up with the form, they were afraid that this might collapse. So at that time, Polanyi used the same idea of Hooke and then showed that if you take sections of take section from this St. Peter's Dome and basically calculate the weight of each section and apply it to a hanging chain, you would get a specific form, and if you reverse that form would actually collapse into be within the section of the St. Peter's. And he showed that as long as that thrust line, he called it, stays within that section, then the structure won't collapse. So this was the main idea behind using hanging chain of Hooke. But probably the architect who actually celebrated that idea and used it extensively in his work was Antoni Gaudi. So he was using the simple physical models that including only strings and sandbags to construct really, really complex structural system, and then using those physical scale models, reversing those ideas, and then sketching on top of that in order to come up with the design of these buildings. Right. More recent example of this, we can refer to the work of Heinz Isler, who is using the same method but in different techniques. So he was actually using wet cloth and in the winter to make them to become frozen, and then reverse them and study the type of form that they got. Or he was using plaster in order to make these plaster models, and he ran lots of structural physical tests in order to find the form of his shells. The interesting thing is that this shell, for instance, has a 50 meter span with thickness of only 4 centimeter concrete, right? But the person who is, I would say, the king of becoming using this technique was Frei Otto. He developed really extensive machinery in order to control all the elements that he had in his design and to basically derive many different structural forms based on physical form finding. But the main drawback of this technique is that the scaling of the material from the scale of a model to the real scale is really difficult. translating the geometry into the actual built geometry would be hard. And if you want to make any changes in your design, you have to build models that might take months to become completed. Besides, the properties of the material, and let's say the behavior of material on a smaller scale, is not always the same if you scale up the material. So that was the reason that around 1970s, people moved towards numerical form finding. One of the most well-known methods in numerical technique is force density, that people are using it a lot in their form finding techniques. But the problem with the force density in terms of design is that you input a network and it works like a black box and you get output out of it. So you don't, as a designer, you do not really understand what's happening within that black box, how to control that form. How can I become master in really manipulating this thing? If I want to make any changes, what should I do? There are other examples, recent examples combined with the use of evolutionary algorithms. So that actually allows designer to play, push and pull the forms to get the best structural performance. But the problem with these methods is that, so it gives you, let's say, the live feedback, but it doesn't tell you how to improve the performance of your structure. For instance, which point you have to pull or which point you have to push in order to get a better form. So it's not, again, it works as a very similar to the force density method or numerical method that works like a black box. And a designer does not really understand what's behind the scene. The third category of form finding called graphical form finding, right? So the graphical form finding dates back to maybe 1725. These are the drawings by a mathematician called Varignon. So he was a French mathematician who was interested in studying the form that are in equilibrium, and then using geometry to calculate the magnitude of the force in those forms. So for instance, if you have this rope that has been pulled from three sides, if you want to find the form, basically the forces in each rope, it's enough to make a polygon that each edge of that polygon is basically parallel to one of these ropes. By closing that polygon, you can say that this system is in equilibrium, and if you measure each length of this polygon, the length of each edge of this polygon, you can basically find the magnitude of the force in each rope. We can simply use this in a convention that is perpendicular to the rope. So you can imagine that if you take a line which is perpendicular to each rope, you can simply construct that closed polygon and basically find equilibrium for that system. Okay? Using this system, using this technique, you can combine multiple nodes and basically you can find the force diagram for your system and basically find the equilibrium of that system geometrically. Okay? So this was the basis for the method that was later called graphic statics. So the first person who put this together in a book was Carl Kuhlmann at ETH Zurich, and he called it Graphische Statik. And then there are other examples of this book that was developed by Cremona and Wolf and many others afterwards. So many people, and engineers, let's say designers, use this technique in order to design their buildings. This is a section, the cross-section, that has been designed again by Guastavino, and this is the section through St. Francis de Sales Roman Catholic in Philadelphia, and this is the built structure based on these techniques. What is quite interesting about graphic statics is that it's being used in many buildings since 1864. So in graphic statics, generally speaking, we have two types of diagram. One diagram, which you can see on your left, is called the form diagram, and that gives you the geometry of your form, the location of the supports, the length of the members, and the line of application of your forces. The other diagram on your right is called the force diagram, and the force diagram will tell you that the forces that are in the form are in equilibrium. There is a one-to-one mapping between the elements of the force diagram and the form diagram. For instance, in this case, each edge of the force diagram is parallel to an edge in the form. The bottom chord that is highlighted in blue in the form has corresponding edges that is highlighted in the force diagram. But the true value of graphic statics is that, well, these two diagrams are reciprocal and geometrically dependent. So if you make a parametric model, then you can simply change the magnitude of the forces and then see those results in the form. Cool thing is that everything is explicit in this technique. So you have a direct control over the magnitude of the forces. But there's another important factor. So you can do really simple optimizations using this technique. For instance, in this example, the force diagram basically is constrained to a circle. And you can see that the edges that are highlighted in blue all have the same length. So those are basically the radii of that circle. That means that you would get a constant force members in the form diagram because the magnitude of the force always is the same in the form. Okay. So this technique is still being used and developed. For instance, this is a design of a convention center in China by SOM. So they were using the same technique, but they were optimizing the use of, for instance, steel in this project. And I'm trying to optimize the volume of the steel using the force diagram, right? So this is the optimized value, and the form is basically is a result of that optimization. This technique has been extended to 2.5D, let's say, because previous examples were always existed in 2D, and if you wanted to make three-dimensional examples, you had to basically put multiple of these sections side by side in order to get two-dimensional structures. But in 2009, Flip-Lock extended this technique to 2.5D, and he was able to design free-form funicular shells. So the technique that he was using is basically separating the equilibrium in horizontal plane and vertical plane. And in horizontal plane, he finds all those polygons of forces that are basically give you the equilibrium of each node, and then translating those magnitude of the forces vertically to get the shape of the shell. So using this technique, you were able to make extremely efficient structural system such as the armadillo walls. If you haven't seen it, please check out that. Well, you can because the Venice Biennale is over. But you're able to really exploit the structural performance and minimize extremely the use of material. This is the stone wall that all the stones are basically sitting side by side, only without any adhesive in between, and they're all in compression. But as an architect or designers, we would like to go beyond shells, so we don't want to stuck in 2.5D. So my task during the PhD was to basically extend these methods to three-dimensional techniques that we can use in 3D, right? So let's just get back to the original idea of 2D form of force diagram. For a single node on the left, we can find the equilibrium of that node by making a closed polygon. That polygon, the length of that edges of that polygon will basically tell us how much force will go into each joint, each member. Okay, but what is the equivalent of this in 3D, right? So I went back and I looked through the history, and I realized that there is a paper that is talking about this equilibrium and these principles in 3D, and it's called Principle of the Equilibrium of Polyhedral Frames. The funny thing was that this publication was only a half-page publication in Philosophical Magazine in 1864 by William John Macklin Rankin. Okay, so this is really funny because the whole publication is only 3 paragraphs, and each paragraph is simply a sentence. So my PhD was basically to go ahead and decipher this paragraph. So in order for you to just realize that how intensely written paragraph it is, I'm just going to read it for you. So it says that theorem, if planes diverging from a point or line be drawn normal to the lines of resistance of the bars of a polyhedral frame, then the faces of a polyhedron whose edges lie in those diverging planes in such a manner that those faces together with the diverging plane which contain, it goes forever till the end of the paragraph. So it's funny because by the time that I was writing my PhD, I realized that I did not understand completely this paragraph, because the second paragraph talks about the topological relationship between form and forces in 3D, and the way that I understood does not make sense with those topological relationships. So I ended up adding another chapter to my PhD, and I realized by the time that I was writing. So the simplified version of what he meant in that incredibly tense paragraph is this. So if you have a three-dimensional bars coming to a node, so for instance, you have a node that there are three nodes connected to that in 3D. If you put planes perpendicular to each member of this three-dimensional frame, those planes together will form an open polyhedron. Do you see that open polyhedron? Okay, they're actually coming to a single point that is highlighted blue in this figure. Okay, the closing face of that open polyhedron will tell you what would be the direction of the force that you can apply to that node and keep it in equilibrium. Okay. Besides, the area of each face will tell you how much force will go into each member. Okay, so you can apply this to general node with more than 3 valencies, and you can find the force polyhedron accordingly and find the equilibrium of that node. So basically, if you want to compare and summarize what I already said for these two frames, one is 2D, one is 3D, is that in 2D you have a node versus a polygon, but in 3D you have a three-dimensional node and a polyhedron. In 2D you would have a length corresponding to the magnitude, but in 3D you have area. Well, you can prove this using the divergence theorem. It's very similar to hydrostatic pressure. But let's see what are the properties of a single force polyhedron. Well, if you have a node that there is a force applied to that, there is a force polyhedron that can represent the equilibrium of that node. And each face of that polyhedron corresponds to one of the members and has a direction that it's a normal direction. And the normal direction basically matches the direction of the force, those members. If you put your thumb in the direction of the normal, by curling your fingers, you can find the edge direction for each face. And the edge direction for two adjacent faces are basically opposite of each other. Okay? So you can use the same technique, the same principle, in order to find the equilibrium for the nodes, that there are forces pulled from that. So the same force polyhedron can represent the nodes that are in equilibrium, except the normal directions would go from each face towards outside, right? So in order to find the forces in the members, it's enough to match the edge vectors for each member with the direction of the normal. For instance, if we assume that the edge vectors are always going towards the node O here, the edge vectors are basically parallel and in the same direction. That means that all these members are going to be in compression. Okay? But what happens if one of the members goes like that? If we compare the edge vector with the normal directions, we realize that we're in the same direction, but they're parallel but in opposite direction. That gives you compression and tension. That's why the same technique can be used in order to explain systems with compression and tension. Okay. Besides, so far, whatever I said was about tetrahedral cells. So the tetrahedral cells are geometrically determinate. That means that there's only one degree of freedom for you to scale it up. So you can't change the faces. You can't scale up the faces without actually changing its direction. And if you only know the magnitude of one face, you're able to find the magnitude of the other faces. So it's quite determinate. But you can have general polyhedrons for the nodes that have more than 3 members coming to them. And that would be an indeterminate force polyhedron. So indeterminate force polyhedron, you can have different values per faces. And the force polyhedron can also be self-intersect. Okay? In that case, the magnitude of the force would be the multiplication of basically the area of each region times its normal direction. So for instance, in this case, if you assume that the positive direction is towards outside of the face here, this is a face, and the magnitude of the force is equal to the area of that. And if you get complex phase or self-intersecting phase, you get two regions with two opposite normal directions. The total magnitude of the force would be the sum of each region times its normal direction. So in this case, because the positive side is bigger than the negative side, you get a positive value for the force. But if you continue by changing the magnitude of the force, you can get negative value. So this is important because for the same form, in indeterminate cases, you can have compression and tension combined system. This is quite interesting from the design point of view. Okay, but now if we know that, okay, each node can represent the equilibrium of each node can be represented by a closed convex polyhedron, let's see how we can attach these polyhedrons to each other, or what would be the meaning of two adjacent nodes in equilibrium in the system. So, as I explained before, we have a positive cell that can represent a compression-only node. So this positive cell can be added to another positive cell from the face that are exactly identical but have opposite face directions. And then together they can represent a system in equilibrium that is compression-only. Okay? But the same thing can happen because we can flip the edges in the form diagram and still be in equilibrium. Our form would be simply flipped. So the same force diagram can represent the equilibrium of a compression and tension combined system, as you can see. Let's just say a positive cell can also be added to a negative cell. A negative cell is a cell that all the face normals are basically facing outside. So by flipping the edges, and you can basically combine one node that was originally in compression and one node which was in tension, and to get a compression tension combined. This was just to show the flexibility of the system in order to describe different structural forces in your form. So that's it. Knowing that, we are able to basically analyze this, the polyhedral frames under given boundary conditions and applied forces. So there's going to be a global force polyhedron that represents the equilibrium of the applied forces to the system, and then that global force polyhedron would be adjacent to nodal systems to basically give you the equilibrium of each node. Okay? So that's it. So this is the whole thing that I'm not going to talk about the technicality of using these techniques. But so far we have a principle that we can work with. So what are the design techniques that we can actually use in this method to generate really interesting stuff? So to show that the flexibility of the system and the equivalency of this system with two-dimensional method, for those who are familiar with two-dimensional graphic statics, this is a compression tension combined form and force diagram in graphic statics, and this would be the three-dimensional equivalent of that you have the three-dimensional, let's say, polyhedral system and its force diagram. To give a little bit of credit to myself, this three-dimensional representation of forces and its force diagram didn't exist since 1864, so exactly 150 years ago. So they were using this technique, but only in two dimension for the past 150 years. Okay, so you can show that each cell in that force diagram basically represents the equilibrium of each node in your system. Okay, so let's talk about the design techniques. The first design technique is aggregation. So if a single force polyhedron, if a closed force polyhedron can represent node in equilibrium, then the aggregation of these polyhedral cells together can represent a group of aggregated cells corresponding to a compression only, for instance, in this case, a spatial network. Okay, so we can have a spatial network according to this force diagram, and we know exactly how much force exists in each node and what is the equilibrium of that, and how much force goes to each member, because the area of each face corresponds to that. Okay, that means that we can aggregate a variety of different polyhedral cells to get different structural solutions. For instance, in this case, I'm aggregating polyhedral cells that are concentric, and the resulting is a shell with non-parallel applied loads. Okay? So you can control the amount of curvature that you have in your system by aggregating, for instance, the pyramids here in this case. They're coming to, not coming to a point, but they're going to the line. And you're basically creating a curved surface that is in equilibrium. Or you can aggregate multi-layers of these polyhedral cells, and then you get spatial systems. Here, in this case, it's a two-layer shell structure, which is in equilibrium. Or the fractal aggregation of these polyhedral cells can result in branching systems. Or the tubular systems can be the result of the radially aggregated polyhedral cells in multi-layers. And you can go beyond that by going fully to three-dimensional by aggregating space-filling polyhedral. Right? So, yeah, as you can see, it gives you a freedom in exploring a variety of structural forms. And the important thing is that in all these examples, you have a control over the form because you already start with a force diagram that guarantees the equilibrium. Okay, so with a little bit of patience, we are able to achieve really interesting designs that was not conventionally possible using these techniques. And by giving a little bit of attention to the design of the force diagram, we always guarantee that the resulting form would be in equilibrium, which is quite interesting. Okay, another technique is basically exactly the opposite version. So for a form of the force diagram in equilibrium, there are some information embedded in the force diagram that we can use. For instance, we can say that the equilibrium of this system, the equilibrium of the external forces applied to the system can be described by this global polygon on your right. Okay? So what happens if you go inside that global polygon and try to subdivide that in order to get different forms? So basically, the topology of your structure is a subdivision of the global force polygon. So that means that you can have a singular, or let's say given boundary condition, and by only subdividing your force diagram or global force polygon, you can derive a variety of interesting structural forms without changing your boundary conditions. And this is quite interesting from design point of view. Okay? So, for instance, in this case, if you have a branching system, you can manipulate or just subdivide your force diagram of the branching, and you get different types of branching structure. You can see that in all the examples that I'm showing, the force diagram doesn't change that much. The only thing that I'm changing is the level of subdivision and combining different methods of subdivisions to get different forms. So you can also combine arches and branching systems and get really interesting structural systems that are all compression only, and they're all in equilibrium according to the force diagram. Then later you can translate, of course, each scheme into the architectural language to start with a concept that originally has some structural meanings, and then work from that point, right? So the same principle holds in 3D. So in 3D, you have this exterior polyhedron that encompasses all these little polyhedrons inside, and that is basically your global force polyhedron. Therefore, you can subdivide the interior space of that, and then you can extract the topology of the form from that. But you can, again, apply different subdivision techniques. Just assume that this is a very simple example, that there is a force applied to a joint, and what I'm going to do is just to get the face that corresponds to the applied force is subdivided into 3 sections. The result would be a topologically different structural form, and your force, your applied force, would be divided into 3 smaller forces to be carried out by your structure. You can also basically explore different methods or ways and techniques for subdivisions, and then you can get different topologically different systems. For instance, in this case, you can start with the simple joint, and then subdividing the top face, you can get the shell that is in equilibrium. So you can also do not touch the exterior faces and just go and subdivide the interior face and get, again, topologically different structural forms. So, yeah. So you remember that I was giving this example of this form on the force diagram in 2D. we can make compression and tension system by adding to compression-only systems just by adding a force in their boundary conditions. For instance, in this case, I actually apply the force P on the joint on the left, and I get a compression-only solution because all the cells, as you can see in the force diagram, are convex. Okay, if all the cells are convex, I can apply the same technique in 3D and apply this force to get the convex cells. And then once I get convex cells, I can start subdividing those convex cells to get more intricate structural forms. Right? So you can apply this in multiple levels and recursively to get really, really intricate structural systems. For instance, this is a three-dimensional branching system and its force diagram showing different layers of polyhedral cells and basically corresponding faces and the magnitude of the forces. By subdividing this force diagram, I can get topologically different form, similar to what I had in 2D. So I'm basically using the information in the force diagram to generate interesting, or let's say variety of different solutions in the form, which might be quite interesting from design point of view, right? So the same thing happens here. I have a compression and tension combined system, and I basically use the same principle and subdividing the force diagram to get compression and tension combined, for instance, truss here, right? So on the left, you can see the same example I was showing at the beginning of this lecture, and on the right, that's a three-dimensional equivalent of that using these techniques. If you remember at the beginning, I said that you can optimize this form and you get a constant force member, let's just say force members in your system by just simply constrain your force diagram to be the radius of the circle. You can do the same thing in 3D, and you can optimize it such that all the forces within the tension part would be the same, and that would be the equivalent of this. Well, in 3D, it slightly would be difficult because you're dealing with faces here, not with edges that you can easily constrain into a circle. So you have to do optimizations. But you can translate this into the language of non-conventional structural systems, right? So for instance, in this case, I did a conceptual study for this bridge, right? Okay, another note on fabrication. So you remember this is a roof of a maritime museum in Netherlands. So they used different optimization techniques first in order to find the form of this shell, and then they use optimization techniques basically to rationalize all these faces to become planar to be coated with glass. Okay, I'm just going to show you a simple node and use basically subdivision techniques and show how these techniques can be used in fabrication. So here is a simple node that is constrained to 3 points A, B, and C subjected to the applied load, and you can see it's force polyhedron. What I'm doing is subdividing the top face of the force polyhedron as well as the side faces, and then you can see that topology of the system will change according to the subdivision. So you can go from a very simple node to a shell, and the most important thing is that the faces of this shell, they're all planar. That's because of the inherent planarity of the form force polyhedrons. Okay? So with a single techniques, you're basically combining two difficult, let's say, computational methods for form finding. So the first one is the form finding, and the second one is rationalization. So with this method, you're combining both, and the result would be fabrication friendly, right? Okay. So this is exactly the same principle. You can also use this technique in a constraint method. So the same rules that people use in 2D graphic statics for the constraint construction of form and force diagram, you have the same in 3D, which all of them applies, right? And for instance, the three-dimensional equivalent of the three-hinged arch in 2D is a shell that is constrained to a plane. As you can see, it's with a dash on the top. The dashed triangle basically shows those planes that this form is constrained to. right? So, but none of, but let's say most of these techniques are not really possible to do with hand, so it's, we need a computational implementation. So currently I'm working on this computational implementation that allows us to start with a force configuration and extract the efficient forms from that. Basically, it gets the topology of the form from this force polyhedrons and makes that topology become perpendicular to each face in the force diagram. Right? So this can be used in order to explore a variety of different structural solutions just by starting with, to design the force diagram. Right? Okay. Not going to go through that, but again, this can be paired with different optimization techniques. For instance, I'm here extracting the form out of a pre-designed force diagram, but the result of this form finding does not give me proper edge length. So in order to get, for instance, you can see that some of the edge length here in this form are quite small, and it's not properly basically propagated through the thing. So I apply another type of optimization on top to make them to basically find a better distribution of the length for the form diagram. So I'm just going to finish my presentation with the recent material investigation that I've been doing. So in order to prove the theory, we certainly need to test it with some material studies. So the whole process of translating these bar node models into volumetric geometry by itself is another realm of research. Because we are dealing with three-dimensional networks, but it's a very interesting area that we are actually exploring currently. This was the workshop that I had in the summer and in Tehran, and then we tried to use the same techniques with the students. They developed different schemes, and they tried to fabricate one of the nodes for their structural concepts. The result was really interesting. So they were they came up with different structural solutions for possible structures to be built. These are some of the examples of these explorations, as you can see. And they also looked at the different methods that they can fabricate each node out of concrete. So each group used different methodology for that and developed their technique. And this is the scene from the construction of the final prototype. So we spent a lot of time to basically fabricate all the joints and members, and these are basically the joints for the actual structure we started to build based on that workshop. And this is a scene that they started to put together. So this is the first built prototype using 3D graphic statics and the method that I explained for you. So it's a prefab concrete construction, and the concrete does not have any reinforcement in terms because we try to minimize the moments that we had in the system, and the form is basically a compression and tension combined system. So on the left you have the assembly process of that. On the right you have a similar structure that was built and designed and built by Gaudi. This is a Colonial Guel church, and you can see that he started to go towards three-dimensional ideas, but he didn't have the right tool to explore various examples. This is the final structure constructed. These are quite recent images. So this is quite unique in terms of the performance, because the top chord of the structure works in tension. It's pure tension, and the bottom parts are basically in compression. So this is the first prototype built using this technique, and this is, I can say, one of the few compression and tension combined spatial structures. I'm going to close my lecture, and this is going to be my last slide. As I said, we are working right now in the name of Polyhedral Structures Lab at University of Pennsylvania. I just started at UPenn 3 months ago, let's just say 4 months ago, and this is quite recent. So yes, if you would like to read more about our work, please visit our website. It's called psl.design.upenn.edu, and I would be ready to take any questions if you have.
Thank you, Masoud. I'm going to open it for questions in the audience. Any? There's one question here.
So, I'm curious, what type of software are you using to for the modeling and exploring those design options?
Yes. So the software I was showing, I'm using Rhino, but there is a prototypical plugin. It's a work in progress that we're working at the lab, and it will be released by the end of the summer. That has been written for Rhino currently. But the only reason that we are using it for Rhino is that that is the most commonly used software at the school. But there are not so many let's say commands that we need from Rhino. So any type of software is possible to be used for this technique. The only thing that we need to have is the ability of that software to be able to model planar surfaces, because we always work with planar surfaces, and the rest is just bar node structure.
You mentioned you're working also in a software that does this type of analysis. Is that also something that's going to be available to the public or not?
Yes. So basically that is, so I have written that prototypical plugin for Rhino, and I'm trying to release it by the end of the summer, and that will be available for public to use. They can start with a force diagram and explore a variety of different solutions in compression and tension. But it's currently, it's been written for Rhino, but there is a possibility to extend that. There's also a platform online. It's called polyhedral on our website, and it's based on WebGL. So right now it's for static only representation. So the models that we generate in Rhino, we just export it as basically WebGL model. Is again based on nodes and members, and we just visualize that online on the website. It's called polyhedral, and I'm working also on that platform to make it possible to turn into a design environment. But running calculations online is really difficult. So that's something that we need to solve for future. Whether we would like to have a standalone software for this, or work with the software as a plugin for different softwares, that's something that we need to explore further. And we need to basically see which one is more efficient in terms of the calculation.
Well, any other questions? Well, I don't see more questions, Masoud. Thank you very much for your time and the amazing presentation and inspiring examples of the work that you're doing. You're welcome to be our speaker again sometime next year to see what new advances and new things you've done on your end. Can we give an applause to that? And
thanks a lot.
Yeah. Thank you very much. You're welcome to.
Thank you. It was a big pleasure. Sorry that I was quite tired today, so it's quite late here. It's like 10. So yeah, please forgive my little bit of typos and yeah, my speech. Forgive that.
No worries. We'll continue with the second part of the presentation with our second speaker, Steve DeWitt with Project Frog. Steve, I'm going to make you the presenter so that our online people can look at your presentation. Let's see. Are you on? I am, yeah. Sorry about that. I'm on mute. Put an extra speaker on somewhere. So your audio is maybe. Yeah. So people in the audience, can you let me know if you hear this? You can just give me a note on the chat line. It should be better. Your mic was on. Sweet. I don't see any response online. I'm assuming that you're hearing me correctly. Is that okay? Okay. Excellent. Thank you.
All right. Good deal. So I'm Steve DeWitt and Johnny Bacola over here. We work together. He'll probably be chiming in as well whenever we've got some additional comments to add. Feel free to ask any questions as we go. One question I just wanted to ask. So lots of people use Dynamo differently. I just wanted to see who here creates models via Dynamo, meaning you're placing families or walls or windows or doors, rooms, or handful. Okay, cool. Good. Maybe there'll be some good information in here for you. Basically, what I really wanted to show, first I'm going to apologize because my PowerPoints were really boring. I don't add colors and I'm not very graphic, believe it or not. I like the software and that's about it. So,
want to maximize? Or?
Yeah, sure. I can't see my bulb. Basically, I was asked to show our use case for Dynamo. I asked Caesar to come and review some scripts that I had written probably about 8 months ago. It was my first time to get into Dynamo, and I wanted to make sure that I was doing things in a way that made sense to somebody who had some more experience in it. So I started as a rookie and basically got him to come in, and he said, this is kind of a cool idea, so when you get a little more experience, why don't you, if you can, come do a presentation, since I think our use for this is significantly different than what I've seen most people use it for. So this is our you'll see our use case, and then we're gonna, after I show the use case, I'll spend some time in just talking about how it's changed how my company at this point is changing and modifying and manipulating families, while I run some Dynamo scripts behind the scenes to show you how we're actually using this in our everyday environment. So, quick disclaimer. So, we literally skipped 16 and hopped into 17 about 3 weeks ago. So there's probably lots of features that I want to incorporate into our current stuff that I'm going to be showing you. So excuse me for not having all the cool new features in what we're about to show. Like there's no global parameters or anything like that. So I should kind of start off. Project Frog, we're a prefab company. So we handle our own shops. We're a componentized system. We deliver a flat packed building. So we have a unique need for our model. And I'll highlight that here in a second. So we also, even though this is free for the public to publish your own nodes, we were a little paranoid that we didn't want to start using custom nodes to begin with. because we really wanted to control any troubleshooting issues that we might have, and we didn't want to rely on somebody else's node if it broke for any rhyme or reason. So you'll see a lot of out-of-the-box nodes in here where there's probably some room for some custom nodes, but that's just how we have handled it. And in the last 2 or 3 months, we've decided to start bringing in some publicly published nodes. So I do kind of want to emphasize a little bit on our model use. So there's, we create one model to drive our manufacturing output. So our models create CNC machine data to fabricate our wall panels. We're getting down to starting to own our shops for windows and openings. So we're in charge of the length of extruded aluminum that we're going to use. So we've got a lot of content that needs to go from the model to a CNC machine. So we create a model that's about a level 400. But at this point, our model right now is creating a bill of material. It's creating what we call a component model, which is like an install guide. So it'd be imagine getting a new outdoor piece of equipment that requires assembly, and you've got an exploded view. We create an exploded view of our building to show the installer how to install, panel by panel by panel. So it's very similar to like a construction sequence for Navisworks, but we do it in just an exploded view. Also, we are extracting our shop drawings out of this as well. And then we additionally create permit sets. We are not always the architect of record, so we create an architectural model for our AOR to utilize and create construction documents from. And then we sign and seal our structural drawings, so we also create a structural model. But what we do is we create one model for all this, and then pieces of this model are just extracted, and then we use those models for all of these different things. So so my use case. Let me show you what we're looking at here. So what we needed to do at Frog is we needed to kind of eliminate some fears that prefab has in general, right? It's not flexible. It's hard to design around because the rules are specific to a building or or an engineer's requirement or whatever the criteria might be, right? So what we wanted to do is create a web application that housed these rules for us so that architects and designers could go to a place and these rules are embedded in a software. Really, we wanted that to be Revit, but we couldn't do that, right? So Revit doesn't, well, maybe so with global parameters, but we wanted to be able to give the designer the opportunity to configure a building and customize it as they see fit, versus them come to us and say, hey, we need a building, we need about this square footage, and not knowing the rules of how they need to design something for us. They can't just give us a model and say, all right, we're gonna take this and what we call frogify it, turn it into a building that would fit our engineering needs, if that makes sense. So what we've done is we've created this web app, right? And it's really simple. You're selecting a building. We're constantly adding new features to this. We've had it released for probably 6 months maybe, and we've had it in use for about 3 to 5, somewhere in there, and practical use for probably the last 3. So I'm going to select what we call a double-loaded building. And so what we do is we've got rules in here, and so I'm dragging as far as I can possibly go. I'm adding links. I'm offsetting the building sizes or the footprints of what we call bar A and bar B. So the idea is we have the rules embedded in this web app. Additionally, Dynamo holds some of these rules, and we'll talk about some of that as well. And so we just really want to create a building. We want whomever to create a building and to customize it however they wish, right? So let's say this is the configuration for whatever reason that I have chosen. At the next step, what you see here is in order for us to give you a design that is structurally sound, we've written our own structural analysis engine, which is what you're seeing down here. It's thinking, it's making sure that we already haven't broken any constraints. The idea is at the beginning stages here, you'll never be able to break constraints, so you'll always be creating a building that's valid. And And so once you get a valid statement here, we can start to add rooms and separators, and really I should call these collector lines. So obviously there's going to be shear walls starting to be placed in some of these walls, depending upon if shear needs to be placed inside of these lines of structure. So here's my wonderful frog building. As it validates, I'll go to my next step. It's grayed out until it actually gives you a valid building. And I'm running through my VPN, or actually no, I'm not. My VPN's going to come up. So yay, we got a valid building. Going to our next stage here. Now we actually configure our building. So what you see here are slots, right? Like, where's my pan? So slots are areas for, or I guess let me start off with, you've got slots that are vacant, and then you've got these dark slots, which are shear walls, right? So at this state, you can't, if you come in here and you select a shear wall and you delete it, it's going to go through the structural analysis engine and basically come back and say, hey, you've deleted a shear wall. That's unacceptable. You need to place shear somewhere else, right? So, we've created a couple different tabs here. We've got shear walls, we've got non-shear walls, we've got openings for doors, we've got openings for windows. And then you just start to add these skews, what we call skews, right? You can call them whatever you want, but you just add these into these different slots. And so, this maximum, say we choose this particular window. This window doesn't give you a size necessarily, but it says it's a full opening of a panel, right? And so the folks who are using this at this time, they know our kit. We've worked with them before, so they have an idea of our system. The screens that popped up earlier that I closed out of, they kind of prompt you to know these things as well. So that would explain, this if you hadn't gotten in before. So the idea is you select one of these skews and you start to place in openings and configure your building however, however you want. You can select them, you can delete them. If I said, all right, I don't want shear wall here, I want to take that out because I want a window there, then I could add a shear wall right there. And if you see, the analysis is going back to the engine to make sure that placing that shear wall there isn't going to do any harm to the integrity of the building. One thing I didn't mention before, when I started this whole, when I started the building, I've got a project set up of an address that has all the seismic criteria already predetermined. So if you give me, what you do as the end user, you say, hey, I've got a project at this address. We look up that data. We assign those fields to that data, and then that's how we know if it's going to be a valid or non-valid building. Does that make sense? So while this is thinking, I'll just do some quick, I'll just drop in a few skews just so you can see. And what I'll do is I'll configure this building here in a second. We'll run it all through Dynamo, and the output is going to be a model that drives all that previous information that I told you about. So let me add in the door just to make it look like it's actually a building. So certain skews are not allowed to go in certain locations. So you'll get little red boxes or little Ghostbuster sign for skews that can't go in certain areas. We've got some consultants that we're working with now that we're going to start configuring buildings for them. So it's not necessarily like this is a frog building, this is a building that we've engineered and designed. So other folks now are asking to create configurations for their specific layouts, right? So we'll add their particular skews if they have certain skews that they want. We're also introducing new features like add a custom opening, and then you can just drop in your size, and then the size basically may not be, well, I guess with our new system, it would actually be graphically shown correctly. But here it's kind of this is not this interface right here is not based off of it's not vector based, right? So it's just representation of what the image might look like. But ultimately, the new vector based system will actually show the correct size opening and whatnot. But this was our first, yeah.
So this interface, the purpose is to put it on the hands of the client, or you coach them?
It's kind of both. So what we've seen so far we've seen kind of two elements. So we've got architects that we've worked with in the past, and they often want to customize our buildings. And so we say, instead of customizing our building, go to this web app, create as many configurations as you want, and then submit those, and that configuration becomes their own building, right, with just our kit of parts. But what also happens is we still got clients that we've never worked with, and we don't want to say, hey, go to this web app and figure it out. They'll give us an idea of what they're looking for, and then our designers will come in, create a configuration, and then we'll get our specific outputs from the web app to create the Dynamo file.
Kind of a proof of concept too at the moment. It's very much in beta right now. But yeah. So it's what works as an internal tool for us to design based on a client.
Yeah, we're getting, we probably get 5 configurations a week, and that's outside of us, and then internally we probably do about 10 just to test it and work on new features that we want to add in. There's silly little bugs here and there that would never get noticed on this end, but on the back end, at the Revit model side, you'd see them. But what you'll see today is hopefully legit, right? So normally you'd come in here and you'd have to place in all your non-shear walls, but to avoid the lengthiness of that, we've set it up to where anything that's not filled out is going to put in a non-shear wall. So just pretend I put in a bunch of non-shear walls to fill out the rest of this. Yeah, so I'll save it. And then what I'm going to do is I'll submit my design. So it's going to revalidate it. It's going to give me a little message here saying that my design has been submitted. And what I'll do is we'll talk about a few items that are somewhat interesting, I think, as far as how using Dynamo for us has changed the way we manipulate families. And so what it's doing right now, so I'll be going back to my machine through VPN here, and I'll be running some Dynamo configurations. I didn't bring it in here first because this machine wouldn't handle it. My Dynamo scripts are pretty long, and there's 4 of them that I have to run. And they take probably about 10 to 15 minutes to run in total length with all 4 lines. So when you see me switching back and forth, I'm not trying to annoy you guys. I'm just trying to get the right configurations. So, all right. So that's our web app, yeah. So basically, the rules live in the web app. The rules also live in Dynamo. We're looking to make all rules in one location, and then extract rules for the web app and Dynamo to be in that one location. So let me go to my machine here, and I should have an email with my configuration files. I do. So basically, we get a, I'm not able to disclose everything. My boss was actually kind of freaking out that we were even doing this. So I'll be glad to answer any questions. I probably can't offer a lot of stuff, so feel free to ask, and then I'll tell you as much as I possibly feel is I'm comfortable with, or that I think you'd be comfortable with. So the idea is now we've got this, this email that comes to us. We've got 3 different configurations, right? Or we've got 4 different files, excuse me, but 3 files that we'll talk about. We've got a CSV file that basically we've predetermined a setup of a CSV file that gives us an output that we can in turn have Dynamo interpret. We also have the structural analysis portion of our design. So this is actually what my structural engineer is using for all of his code calculations for it to be used in construction documents. So basically what I'm going to do is I'll take all these files, I'm going to copy them to a folder that I've already set up, and now this is I have a Revit template behind here, and what I do is I go and I'll find, I don't even remember where I put these. Wait, yeah, I do. Sorry. UI configurations. All right, so I'll take this first CSV file. The first script runs pretty quick, so we'll probably talk through it. But this email having these three elements in it. There's the UI file, which kind of defines the building footprint. And then because I know what window we chose, right? We chose the opening that was offset, 7 feet off the ground, and it was a full panel opening. Well, because I know that window, I also happen to know that location of the window because we placed it in a slot, right? And then because I know what window I chose, that also tells me what panel I should be using, right? So in some cases, if it's a custom opening, it's just the opening size is going to adjust, right? So we built some parametric wall panel families that basically automatically adjust to the different sizes of the openings that any one user can define. And then let me see if it's done. Yes. All right, so first one is done. Let me get the other one running. And this second one will take some time. All right. And so it takes about a minute to open. It takes about 4 minutes to run. Oh yeah, sorry. So what I did want to show you in here is the this PNG file. So it spits out just a quick shot of the configuration that we created. We realized about halfway, through beta testing, I was like, I have no idea what these guys have submitted, and I have no idea if the data that's coming to me is anywhere close to accurate. So we got a little image file just to kind of compare to. One thing I didn't mention in here is you can control door swings, things like that, because we've got, because of the use of our model, and let me see if Dynamo's open, and then I can run this, and I can, all right. So we'll run this configure again, and I've extracted these into separate nodes because the length of time it takes to run these, and it's impossible to troubleshoot anything when it takes 15 minutes to run one configuration, right? So yeah, we basically just wanted to create an environment that a user could come in and get an accurate model, something quick, something usable, and something that's CD ready. So let's see. Yep, sorry, one more. So I kind of showed a slide similar to this. So basically the idea is we've got a web application that has inputs, right? And that tells me what windows and what doors they've selected, where my shear wall locations are, and where my all my non-shear walls are located. And basically that information is given to us in a CSV in two different formats. Like I said, one is just for building configuration, and the other one is almost just as important as the building configuration because they're all the variables that can change depending upon where you build your site, right? So, as seismic criteria change, as you build across the world, we've got more and less fasteners that go into roofs depending on loads, right? So those variables are given to me in a separate configuration CSV that is then assigned to geometry inside of our Revit model that does all of our calculations for us, right? So let's take a metal deck roof system for an example, right? There's two different properties that could change from one site to another, right? Two different styles of fasteners that, in our case particularly, and so those variables that the SAE understands those values, and then the web app gives me that data, right? So it knows which pieces of information to go grab from the SAE so that I can then assign those values to those particular components. So if I have a length of 10 feet, I've got a 1 foot on center spacing, it knows that it needs to be fastened in 10 times however many panels there might be. So those are the three main files that are coming out, two that we use. So Dynamo creates the Revit model, and then once again it's creating a manufacturing BOM, a component model, shop drawings, and then additionally the web app now, because we've got a structural analysis engine backing up the web app, it also gives us our structural calcs, which we didn't have before, and then creating the same elements. But the in between now is Dynamo taking that information in and interpreting the rules that we've established for this particular engineered product. So my outputs, we primarily focused on I'm sorry, I'm going to go back just to verify that I'm not, oh, still going. Yep. All right, so my outputs here are mostly frog scope at the beginning stages, right? So our scope varies every project we go, every project we're involved with, but in general, our scope is openings. We cover doors and windows and framed openings. Not all doors, not all openings, but we still have to model the elements that aren't ours in some cases in order to create an architectural model that can be used for construction documents, right? So you'll see elements in here that are not our scope, but that are also also have a need in order for the architect to create construction drawings. So panels as well, wall panels and roof panels, beams, structural connectors. So anything that ties our system together is also our scope. And we'll talk a little bit about structural connectors and how there's some families that I think are probably a different way to look at families. Miscellaneous fasteners, both modeled and not modeled. I was talking to you a little bit about that a second ago. We're a product company, so we have our own lighting system. So we add our own lighting systems in there, and then some basic annotations. We also, non-frog scope items that Dynamo is outputting are foundations and finished walls, doors, windows, soffits, and annotations. So like I was saying, there's some duplicate of effort here where we're actually doing some of the AOR's work, but ultimately we want to try to play as friendly as we possibly can. Still running. Good timing. All right. So you'll have to excuse my, I have to hit true here twice, and then that's my, this is my bad script. My other ones work well. All right. So, so just to kind of kill some time, I was going to talk about how several of our families now we're incorporating parameters that are specifically for Dynamo. They're not used for anything else. They're not used to drive geometry. They're not used to create a part number or anything like that, right? It's just a parameter that is inside of Revit now that is being used by Dynamo only, right? And so I'll give you a little example. And so we're in the building we just looked at, there's probably well over 300, 400 different parts, right? So that could be a window or a wall panel or a beam or any of the elements that we mentioned before. And so I'm having to place these elements, I'm having to rotate these items, make sure that they align to the, to the outside face of sheathing, so that everything's in its, accurate location. So I'm rotating elements way too much, right? And if you've ever dealt with placing families and rotating them in the Revit, there's quite a few ways to do that inside of Dynamo. You can find your, you can grab the length of the element, and then you can find your vector point. There's just quite a few different ways to deal with it. So in the case that I'm going to show you, I've created a little dummy example of how this is going to work. But in scenarios where you've got an origin point that is not in the center line of your element that you're placing or rotating, your rotation point is not. It's not going to end up exactly where you want that. So these parameters now that are specific to the element are going to help you define that rotation point just by creating a formula inside of Revit to calculate that, or a formula inside of the family in order to calculate that rotation point. Additionally, I was going to talk about instance parameters. Now, in my prior life, I worked at a firm that was more traditional, meaning we had lots of rules like don't use instance parameters. Not just instance parameters, but we've taken out the flip command in our doors and windows. We've taken out the rotate command in our doors and windows, because if you flip a door, it's not the same door, right? I mean, for us it might be the same type, or for a traditional architecture firm it might be the same type. But truly, the hardware is on the other side now, or maybe if you've got a window with a side light, the mirroring of an element means that the actual component is actually flipped, right? So there's no such thing as a mirrored component in our terms, right? So we've taken out some of these functionalities, which is probably, like I said, typically a bad practice, but we had to do that in order to maintain any kind of sanity to think that what we've placed is actually what we're getting. And then next, when we talk about graphic changes, one of the things that I wanted to do is, in order for me to have, if we've already, in this one configuration, you'll see there's hundreds and hundreds of components already. So in order for me to not have to manage hundreds of different families and create hundreds of different if-then statements for Dynamo to select the proper family, depending on what configuration the building is, I've done a big no-no, but it's working out very well for us at this point, is I have like one family to kind of rule them all, right? So I have one door. I have literally, I have one wall panel, or not, excuse me, not true. I have one metal deck panel. I have one of just about everything, but I have a ridiculous amount of on-off graphics that Dynamo, that are all instance parameters that Dynamo reads and then turns on and off depending upon where it lies within the building. And then what we do from that is I can take those instance parameters, and through Dynamo I read all the unique items that are part of, how do I say this? So I'll take the unique items that are similar to one another, I'll identify those, and then I'll create a new family with type parameters based off of those instances. And I'll show you an example of that as well. I did that because once this goes into production, there's still always a little work that needs to get done inside of the model. So I don't want my users to go in there and accidentally select the family, change the instance, and then copy it somewhere else, because that instance is specific to that exact location in order for part numbers to read right for us. So, and I'm sorry, I know probably some of this is like, what are you talking about? But I hope some of the examples are going to make sense. All right. Now, that's normal, believe it or not, just for now. Let me do minimize, then I'll run it one more time, and then I've got two other notes to run after that. All right, so the example that I'd like to show real quick is the rotation point, right? So I'm going to show you two families. One family is symmetrical, right? So the origin or the insertion point, which is the insertion point, which is also the rotation point, is at the very center. So anytime I ever rotate a family that's symmetrical, you never have to worry about it landing in the right spot. It's always going to be there. And then we're going to do an asymmetrical part. And then what I do in this case is if the origin is not in the center, then I've got a parameter, the yellow highlighted one here, that basically is just a formula-driven piece of information that is going to enable me to place either place the element at a different location and then rotate it, and or give me the vector point of which I do need to rotate from. It just depends on the family. In this case, I'm just going to do the simple element set rotation, I think, is what you'll see. So my example is, let me see if this is done. Nope. So my example is here. So sorry, let me do one thing. Actually, wait. Yeah, I wanted to disconnect these. All right, so I'm going to show you first element that's going to place is going to be my symmetrical family. It's just a box. This is just purely to kind of show you the issue. So placed it in the middle. If we dimension this, it's it's exactly like we want, right? Both of them. Now we're going to place an asymmetrical element with no rotation, right? So yeah, so with no rotation. So obviously it's not smack dab in the middle. Next one we'll do is the asymmetrical with a rotation point. So it's still in the wrong location, right? So now what we do is we'll take the parameter that that was part of the family that part of the formula that I had described earlier, and when we run this one, now we'll get it in the right location. So this is the asymmetrical, this is the asymmetrical one, but now we've got it in the exact center point. So we're doing that this isn't necessarily just with rotation, right? This applies to all kinds of different ways to pull information for it to read in the right location, or maybe to even find elements that are around certain components, so that we can define if something is too close to another adjacent, if there's any adjacency issues that we have to be concerned with. So there's, we're using the same logic all over the place. All right, one more, and then that one's done. So, we're using similar logic across the board, right? And that was just kind of a little lame example, but basically all I'm doing is I'm finding that parameter, that 6-inch offset. So if we go back to that PowerPoint, you'll see that just happened to be the value that I was looking for, right? 6 inches. Okay, so next, let's see. Sorry. All right, so now we'll look at some instance parameters, and then we'll create some new family types from those instance parameters. And my example is this. This machine is pretty slow, so I'm trying to bear with it. All right. So what we're going to look at here is a structural connector. So I chose this one because it's kind of the smallest of the gnarly families that are single family instance parameter driven. So might be overkill, but the idea is anything that says default is an instance parameter. So that instance parameter controls that specific item, and so on, right? So I can get those. I place these components, and Dynamo reads a rule that basically defines what items or what elements should be turned on and off. In this particular case, these are nested families, nested shared families that just have on-off graphics, right? In some cases, you might actually have modeled geometry that is not, is not a shared family, and that's driving that information. But in this particular case, we have nested families that have graphics tied to them. And so I want to make sure, there were a few things I wanted to make sure to get out of the right. Let's see. Okay. All right. So my next node. Sorry, I want to make sure this finishes so we can at least see the end result. Any questions by any chance? Is there anything that...
So by the virtue of switching off those elements, you also exclude them from schedules?
No. Oh, yes. Yes, correct. Yeah, good question. So the bill of material is probably one of the most important items that we get out of the model. So that anything that we do has to incorporate a successful bill of material, right? And so that was, we've decided to do things several different ways just to kind of see what the best method might be. But this one just happens to use nested families. But yes, it does exclude those from our schedules. All right, so we'll run this one, minimize. All right, so let's see. All right, so first I'm going to run my script. And what all it's going to do is, I built a random configuration before the class, and I'm only placing in these connectors. So, like I was saying, it's evaluating the rules of our system, and it's evaluating the building configuration. And so it's placed in all of these different families, right? So if I select this and say select all instances, selects every single one, right? But as you notice, they're different, right? They look different. They have different properties that go on and off. So that's obviously the on-off graphics. And so what I'd like, so because we've created these different types now, let me show you my family list here. So here are the two families, right? We have this family is called glue lamb hanger, and now I've created another glue lamb hanger, but these are type properties. So if we look at these are all instance-based, right? And then now we've got type-based parameters that is a separate family, right? So Dynamo can create the family for you if you want. I didn't do that, obviously. So,
so you're saying you go back in and resubstitute. You have another path where you resubstitute something that's not all instances. You know, here you go, you put in the fairy tale, and then you go back in and put in the solid.
Yeah, and Dynamo will do that.
Yeah.
Right. I'll just replace elements that have the same properties. And so that's one thing that's kind of cool about it is you go and, I mean, if they're driven off the same shared parameters, you're just matching shared. If this shared parameter exists and it's a yes, and this shared parameter exists and it's yes, then replace with this family, right? So you're not having to go and like isolate out elements and pick things. It's just finding the same data and then moving it to a type parameter. And this one's probably done. It is. All right, and we'll run our last one, and then I'll stop boring you with that. This one will take a minute to open, probably. It's a relatively big one. Where was I? So Dynamo now. So basically, we've just noticed, like right here, we've got one family, right? So you'll see more populate when it creates them. But the idea is I can come in now and this, where am I? Oh, I haven't ran it yet. So here are, so here's each, so we had 5 graphic parameters, right? So we have 1, 2, 3, 6. Where am I at 6? Did I have 6? Am I wrong? I had 6, I thought I had 5. 1, 2, 3, 4, 5. What's my 6th one? I'm curious now. Side, left side, right side, through bolt, flag. What's my 6th one? Well, I can assure you it works because I've been using it for about 6 months now. What is it? Left, right. All right, before I waste your time, that's kind of a moot point, but I promise you that's, so I now have all my different, oh, I gotta run it, sorry. So I'll set this to true, I'll run, you'll see my family generate down here. All right, so there were only 3 separate types that were generated in a, there could have been 6, I think there could have been 8 possible configurations, but there were only 3 used in this particular model. So then I can go and replace those instance parameters with type, right? So it gives me the benefit of not managing hundreds and hundreds of families and not having to create lots of if-then statements. So you know, anytime we get into lots of if-then statements, we just create Python. No, we just create Python scripts for it, just because it's kind of cumbersome to do. All right, this is all right. Let me set this up. This is the last run I got to do. So let's see. Is there anything I wanted to talk about in here? True. So once again, same logic applies for other pieces of equipment. It just may not be it may not be used in this exact scenario, but we're using the on-off parameters to create one family, and then we also create types from those. And one of the things that I think is, it's going to sound weird, but it's a great benefit, is I have the luxury of not having any human interaction at the very beginning of a project, right? So besides the fact that the web app is the human interaction and they configure a building, but they can't mess it up, right? The web app is controlled, it's constrained, they give me the information and it comes straight into Dynamo. So I have the ability to not, to trust in the fact that Dynamo is going to place these items in the right location as long as my rules are set up accurately. So That's why I think we can do this and get away with it initially, right? I wouldn't, I don't think anyone would ever preach this, hey, let's build one family to rule everything. That's not the best way. So that's why I feel like we can do this. So let's see. Okay, so some of these are going to be very obvious, I know, but some of the lessons that we've learned, if you're ever filtering in Dynamo, quotation marks or inch marks cause problems when filtering. I'm sure I see a couple smiles in the room, so I think you guys have probably understood that before. And this is like the most broad statement you could possibly make, but specific parts of your family need to be highly organized depending on how you're manipulating that family. That seems to be very obvious. Rotation. I spent lots of time figuring out best ways to make the rotation elements work accurately, and embedding that information inside of your family it eliminates about 5 other nodes that would have to interpret where that insertion or rotation point would be. So embedding that in gives me 1 node that I'm able to utilize. So that was a big one. Anyone ever use the scope if statement? Good, because it doesn't work and it crashes all the time. So use the logic if. So if you've got 3 if statements: scope if, logic if, and if, right? The logic if passes the true length of any list. If statement is only going to pass the shortest list that it can pass through. So if you have 2 lists, one list is 3 items and the other list is 200 items, and your if statement should read the 200 items, it's only going to list the first 3 of that 200 items. So that was a big one for me, and it's weird. I don't even understand why it's like that, but I don't write this. So lessons learned: managing one family makes it easier on me, and that's all I really care about. That's true. All right, so hopefully Dynamo should be done by now. Let's see. Nope. Might be another minute or so, maybe less. See if there's anything else in my PowerPoint that I missed.
So to what extent did you use this out-of-the-box nodes and your custom Python?
I'd say the out-of-the-box nodes are probably 85%. Some of the nodes that we do use are from Clockwork. And then from CADRAF, I think. I'd have to see which other components there, but I think they were filtering for location points, where you've got one family instance, and then it gives you everything you can possibly know about it. Is it rotated? What's its origin point? That sort of thing. So it's 85% out of the box nodes. We've written 4 Python scripts, I think, for some of our more gnarly geometry, for some of our more gnarly rules, I should say.
We had to kind of de-abstract, or the data we get from the web app's abstracted, and we have to map it to real families. So we have a couple of external reference files that kind of used to Python. Python's easier to grab a file, a CSV or an Excel file, and read a bunch of data in. So,
yeah. And so here's what you get. I've got something that let's see through here. Yeah. So here's what you get. You get a fabrication ready, model. It's got every single wall panel, every single opening. It's got a complete bill of material. Lighting systems, everything that I listed before. And basically the idea is we take this and we upload it to A360, and then we can do it one of 2 ways. We either leave the components in there, like the wall panels and all of that, or we extract that out and just give you an architectural model. Or if it's, we can basically extract it however you want. So we do have one more script that would run that would take all of these components out that we don't want to share because it's kind of proprietary. And if you look at this family, it's absolutely absurd what's going on in here. It's so we don't really want to give away all of this. I mean, it's thousands of conditional statements that basically our purpose is we've got to write this to a CNC machine. So everything has to know where it is in in space, in time, and then in what order of operations it needs to get cut at, right? So there's just an incredible amount of information that is needed in order to create that CNC machine data. So if you were to look at some of these parameters, it's it's quite lengthy, lots of formulas, lots and lots of formulas. And so we don't necessarily want to give all that away. I'm sure we would if we had to get a job, but this is our whole entire kit. We've got a bill of material now that is ready to go, and then we've written a plugin that basically connects to our PLM system, and it extracts all these quantities in one shot, creates a bill of material that our GC can go read, or that our supply chain can go evaluate and go procure at for other different manufacturers. But this was our use case, right? So when I got to Frog, I was like, Dynamo, 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 and it took me about 1.5 years to get buy-in on it. And then when I got buy-in, everyone's like, dude, this is it. This is what we've been waiting for. Because years before, I guess right when I got there, they were actually, you guys would hate this. We were building architectural models in SolidWorks, right? Like that's the nightmare of nightmares. If you've ever tried to get a good-looking CD set out of SolidWorks, it's just not going to happen. Do you remember? You interned there for a little while.
When I was there, it was rough.
That's because we were cool then, I guess. Yeah. But so So we've got a couple of rock stars there that have been keeping Revit alive. But Dynamo has really changed how we can integrate now with our clients, right? I mean, and Johnny made a good point. Like this is our beta. This is our start. You wouldn't believe the amount of feedback we've gotten from other people that weren't even related to us before that want to create a configuration software for them, right? So that we can just panelize any system and do a flat pack system, or to actually do modules. And it's changed how we've been able to talk to our clients to deal with designers. It's been really cool. Oh yeah, and I should get a shout out to Thomas over there. He was the first person that we're like, please, can we get an intern to work with Dynamo? He worked with Dynamo, came up with a good proof of concept, and then that's one of the first legs of the race that we have. So that's it in a nutshell. Feel free to ask any questions. I'll be glad to tell you whatever I possibly can.
This is awesome. What's next? Where do you see this going?
Oh, so I think one of our biggest. I mean, there's certain things we can't talk about. There's certain things that we can't talk about that are really, really exciting.
Well, I think
next year we can tell you maybe.
The next logical thing to do is automate the clicking process, right?
Yeah.
It's already there.
Yeah.
It's like scripted building.
Yeah. Get rid of the having.
Even though it only takes 15 minutes to do, it's still like if we were to scale up to a point where we need fully flexible buildings, and if you wanted to make 20 a day, this would kind of be.
We hate humans, so we want an interaction at all.
It's dimwits out of business, huh?
And not at all. It's nothing like that. And see, I think one of the things that this has also enabled us to do is our designers, our talented architects, our talented designers, everyone that's there, they're not having to create construction documents anymore, which is I'd say an entry-level style need, right? And we don't want somebody that we're paying X amount of dollars that has X amount of experience to do that sort of thing, right? So now we can generate these models, and what they're focusing on now is product improvements, right? So it's not like, okay, if this bucket connector doesn't look pretty, let's figure out something else to put there, right? And maybe it's not something that we're buying off the shelf, maybe it's something we're creating, because we're a parts company. We've got mechanical engineers, we've got other folks that can create components that are specific to our kit, right? But I think one of the things that is exciting me the most that I can talk about is we're getting companies from other countries now that are coming to us saying, I want you to create a configuration platform for us, right? Here's the idea, here's the building footprint that we're looking to achieve. How can we set this up so it's similar so that I can drop windows, or maybe not windows, maybe it's rooms, maybe it's, we're working with companies in Switzerland right now that basically want to be able to drop in ORs and different medical rooms, and and we can come with the same logic that we've applied here, but we can also, do this on a room-to-room basis, not just on an individual panel or an individual SKU. So I think that's what's been exciting to me. And the fact that it worked was awesome. I feel like I just moved here from Texas, so I was like, all right, I think I'm okay for a job for another year. I mean, I don't know, maybe not. I think that's been one of the things that's been exhilarating to me. It's also gotten our structural team to create a structural analysis software, right? I mean, you should see this thing. It's ridiculous how, the amount of formulas that are being driven just to calculate a simple building like this. But it's the same logic. We'll just apply it to another building, right? I mean, anything that's hard to find in here, we just change. We've got to. We're figuring out ways now that none of this is truly hard-coded anymore, right? I don't care what size panel it is. If it's 8 foot, 10 foot, 12 foot, it doesn't matter to me anymore, right? Any of this can happen at any different size. The building can stretch. So in Dynamo, or at least in the model creation portion of this, I don't care what rules apply. I just need Dynamo to house those rules, and then I can push out any random configuration that I want if we know enough about the building, right? If we have it engineered. It's not something you just it's not a design build project at all, right? It's something you've got to engineer and spend time on and, really make sure you've got all your parts and pieces, set up. And then dividing out scope, everything from fasteners, because then one of the main portions here that a lot of people ask questions in construction is, well, what is our scope, right? So, I mean, I can show you our scope here, but there's fasteners and fasteners in our details that who owns those? How do they order those, right? And so we're able to really delineate scope much cleaner now because we've got complete control of creating the model from the very, very beginning, right? We're not getting a model from somebody and then we're taking their information and then having to manipulate it to meet our pre-engineered building. It's us from the beginning. I go on. It's exciting to me. So yeah.
I did have a question. Not a Dynamo question. It was more a project law question. Cool. I checked out your website prior to the lecture. Mm-hmm. And I saw that it seemed most of the buildings you did were on the website were 1 or 2 stories. Yes. Is there a story limitation that you guys do with panel systems, or can
so right now, what you saw a second ago was just 1 stories, single loaded and double loaded. I think probably about 3 to 5 months, we'll have our 2-story available to configure, just like in the web app. And the consultants that we're working with now are high rise. So it's light gauge steel. It's totally different ballgame. So we're like I said, steel systems. Yeah, the philosophy hasn't changed. I think it can still be handled the same way. It's it's steel or it's wood. It doesn't matter to me. It's going to be I'm going to try to handle it in a similar way. Thanks for asking. Yeah.
Have you done a cost or time comparison with the traditional method?
Yes. So if I were to give you that answer and you were the board, we'd say about 6 weeks. The reality is probably about 3 to maybe 4 weeks that we've taken out in 15 minutes. And I'd say half of that is to get a structural engineer that isn't busy doing something else to validate where shear walls should be, right? So that might take one of our structural engineers a week to 2 weeks. And then it's going to take one of our architects to panelize a system that maybe is custom, to build a model. It's going to take them at least a week, maybe 2 weeks, depending on the series of customizations that they've made. So reality, probably 4 weeks.
4 weeks to get the shop drawing back.
Yeah, and so now we're shop ready right here. I mean, don't get me wrong. It's not like perfect. There are certain components that, like as an example, we have placeholders, right? So we've allotted window types and door types that we may not have a specific wall panel for yet. But what I do is I put a placeholder in, and we call that a .99. So any family in here that has a .99, which looks like this one might be, this is what we classify as a placeholder. And so what will happen is, give me that panel. Yes. So this 299 ultimately has a parameter that's embedded in it that says what SKU was it placed for. And so then I know the skew rough opening, and so I can create a panel based off of that, right? So we've created placeholders just so we can offer more types, because we don't know what people are going to want to use, right? I mean, in certain districts, we do mostly schools for, under these configurations right now. So certain schools might have a certain opening that they have to use. And so the custom SKUs that we'll be adding, you just type in the size, and in theory, the panel would parametrically adjust to that size, to that rough opening. Yeah.
Just curious about the flexibility of your web app.
Mm-hmm.
They work with curved buildings as well?
Not yet.
Okay.
Not yet. But everything is on the horizon.
Okay.
We're about to get our first. No, true. I think we've got one intern that's a software developer coming in. We've got one full-time employee coming in that's a full software developer. So it's all about to change for us. We went from a modular company to modular in technology, I feel like now. So I think and if you want to pay us for it, bring it. We'll do it. We could study it, but if we could have if we get a designer, we get somebody to that has a certain building configuration, we could make it happen.
What are your thoughts about how this is going to change the nature of how we practice architecture? Because this is certainly not traditional deliverable.
Mm-hmm.
Certainly it's aligning with what the future might be.
Mm-hmm.
And so what can a regular architect could do to get prepared to this type of
change?
Yeah.
Yeah. And are you just talking modular in general, or are you talking, are you saying how would this affect like all firms?
Yeah, because I imagine this type of deliverable might be. I mean, it will be the future of delivering products to clients. I mean,
yeah.
you're certainly leading that research into that type of realm.
It's such a hard question. I really don't know. And I do feel like as I don't want to say it this way, but I'm going to say it, as the older generation goes and the newer generation comes up, there's just more acceptance to this. I mean, 10 years ago, 15 years ago, was anybody talking about parametric design? Maybe in school, maybe in class, but not a lot in practice, right? So I think as the younger generation comes up, there's more openness to it. And obviously technology has been a big factor in this, right? I mean, the fact that I can literally give my manufacturer that Revit file, and they extract the information straight to a CNC machine, that wasn't there 10 years ago. And if it was, you had a lot of software development into it, right? I made zero. This is literally just a Revit family that is completely parametric, that knows everything about what a CNC machine might need to extract it, right? So I think it's just, the younger generation, really focusing on parametric design and computational design. The technology is a big advancement. And then as manufacturers start to wisen up and realize that if they do have a CNC machine, I mean, we've gone to vendors before that have like, a $250,000 CNC machine, but you've still got, Frank Johnson out there, like, chopping the wood, and it's like there's a CNC machine right here, but they don't utilize all the features that it might have, right? So I think it's a generational thing. That's the major holdup, I feel like, right now. And then obviously you've got the efforts of, going through documentation and, changing the way that, like if we were at 50% CD and we're configuring a building for you, and you're like, you know what, I want to take this wall and I want a garage door opening that spans 2 or 3 full panels. It's like, sorry, we're already in manufacturing. These things are, stacked in a warehouse right now, ready to be shipped. So it's like, yes, you can do it, but there's, the implications obviously increase as you go down the road. So, I think that's also, I should say, that's probably a pretty big portion of it as well, right? Generational gap, but more importantly, getting the construction teams and getting the design, all that, finding maybe like an IPD project would kind of be a great scenario for things like this, right? Where, your design is pretty much set in stone, and then you can panelize from that, right? We've also got into some areas where we don't configure a building. where I get a model that just has a window in it, and then from the window I can panelize around the window and then make assumptions at certain links because I can pull information from Dynamo on start points and end points of walls. So it's just with the way now that I'm able to extract information from the model and get accurate locations of elements, there's it just keeps getting better and better and better. And that's why I made the disclaimer before. We skipped 16 to come to 17, and 17 with global parameters. I think that's a game changer for Revit in general, right? Like you can just do it. You can do a little bit of everything.
It went down.
Oh. 7:30. Wow. That's too bad.
Some of the drawings generated. You mentioned shop drawings.
I didn't put them in here. That's one of the things I was told not to talk about.
They're in Fusion Lifecycle, our PLM system. So those part numbers that get generated.
He was talking about architectural set, I think, right?
Drawing, whatever drawings.
Yeah. Yeah.
Well, the shop drawings are all in the cloud. They're related to those part numbers, but yeah.
So I could tell you had a question there. So some of our parts, and I'll see you. Thanks. So some of our parts are already predetermined, right? Like we've engineered a panel that fits in a specific window, and that already has a shop drawing assigned to it, and then therefore is updated into a PLM system. So most architects, do you guys know what a PLM system is? Product lifecycle management. So basically, it holds a shop drawing. It's in the cloud, and then I can ask 5 different manufacturers to put a bid on that particular component. Okay. Right. So some of them are predefined, and then in some cases they're generated automatically. It just depends if, like on the 9.9 element I was showing you here, we don't have a shop drawing for that because that's a placeholder. But when we turn that into a shop, we have a process that basically automatically creates that shop drawing. There's certain things that are still manual, like having to dimension things, but that's what hopefully our intern this year is going to tackle. But I took out the specific architectural and structural set. And to be truthful, it's the amount of annotation that I'm doing for the architectural set and construction set is very minimal at this point because I literally just went to 17, and in the version that I was in 15, which was like 1 point whatever, there weren't nearly as many features to create annotation. Yeah.
So just from a designer perspective, from the workflow, say the designer create a concept through the web app, and then load it through the Dynamo script, and Dynamo script generate this whole set of drawings in a fairly short amount of time. But what if how does the designer to modify the design, to update the design? Do they have to go through the web app again?
Good question.
They just
jumping. We're not 100% sure how that's going to work, to be truthful. That's one element that we're still trying to troubleshoot. So our first shot at this is we are going to set constraints in the Revit model, right? And so if as an example, if I were to upload this to BIM Collaborate, I can own those elements, right, as a project frog, right? So no one can manipulate those things, or at least give me notification that something has been modified, right? And either way, if we get a notification that something has changed, or if we own that element, that's at least the start. But we don't. That's a great question. Like I said, we've got 2 models that are out being used in the real world right now. And in those particular cases, we've just told them, hey, the building layout is set. Your properties, or your role is to create the finishes, right? Or your role is to drop in casework or whatever it is. And so they know that they shouldn't be manipulating things. So what we'll do is we'll actually just lock those things down. And I hate to say it, we'll pin stuff. I don't really like doing that, but it's ultimately what we have to do in order for the user to know that they are making a change that could affect the shops, or that could affect the overall layout, right? You can't move a wall. You can't move this wall 2 or 3 inches in any direction because it sets under the beam. It's tied in under the beam. It's where shear walls are located. You just can't do it. So we've talked about a couple different ways, but we've also, I think one thing that we're focusing on is we're trying to figure out a way to create a series of tools that are inside of Revit that don't allow you to mirror or rotate, or like I was telling you, I had to take out those commands inside of our families because a mirrored element is actually another part. So we're actually trying to disable some of those functionalities, right? See, Thomas? Yeah.
So I have a question. So it looks like your web app is built for a perfectly flat plane.
Mm-hmm.
But with sites, you usually
So isn't
it's
not always like that, you're saying? Or?
No.
Oh, okay.
Perfect world, maybe, not in real world. But so how do you take care of, let's say, do you guys do site surveys or something to make sure that there's like hilly terrain? Because if you make it a perfect rectangle, I guess the site doesn't fit.
That's specific. If there's a condition like that, then it's just handled on an individual basis. We don't have any way to accommodate to show terrain or to show like a retaining wall or because at this we sign and seal structural, but we don't sign and seal foundation. So foundation is actually another scope because we can't prefab any of that. Maybe you could do rebar, but that's arguable. So we don't have a solution for that. But that question has been asked many times, and so I know it's on our radar. Cool. Well, thanks, y'all, for the good questions.
Good job. And I'll post this probably next week. Thank you, guys on the line.
And then we lost audio like about an hour ago.
What's up, dude? Yeah, pretty cool, huh? I thought so too.